reading, just getting set up here and looking at question 1. So the cost of materials in dollars for a certain rectangular box with base dimensions L feet and W feet is given by this formula. Is that a function? Did I define a function there?
No.
No, it's just a formula. It's just a formula that tells you what the cost is, right? Cost equals 4LW plus 288 over L plus 96 over W, okay? We want to consider 3 boxes with the following dimensions. Box number 1, number 2, and number 3. Those are the dimensions in feet, length and width for each box. So I want you to study this long expression that I wrote here. And when I put all that in, graphing calculator told me that was 772.442. And the question is, what does that expression represent? Slash or and compute. What does the following expression represent and compute? So study that expression, and you want to type out. So you're not going to use the word plus in there, okay? It's what this basically what that expression represents is what this number means, right? So I want you to explain what that number means or what that expression represents, without saying it's this plus this plus this. Okay? Go, everyone, do that. Think about that. If you want to talk to the person next to you, you can. Yeah. Oh yeah. Thank you. Change that to a 4. That right there, that was supposed to be 4. Thanks. What I've highlighted in blue, let's change it from a 6 to a 4. So now it's 708.44. Okay, let's hear a few of you tell me what you think that expression represents. Yes, sir?
Is it the total cost of materials for all 3 of the boxes?
He wants the total cost of materials if we made all 3 boxes. He likes it. What do we think? All right, so if you said something like that, yeah, that's correct. It'd be that if we made each box, one of each box, it'd be that this is the total cost for all those materials. Okay, so now question 2. In that, so you've got a red, I've given you a red command line there. It's define a function named G, capital G, that gives the cost of a box with width W and length L. So as you do this, when you want to type the parentheses for function notation, you don't hit Shift 9, you use Control 9. Okay, because we know that function notation is not multiplication, right? If you use Shift 9, there's a risk that it's going to just think you want to multiply 2 things together. So to distinguish, GC wants you to use Control 9 to set up that function notation, those parentheses for function notation. That's the first thing. And so now this is an example where we're seeing 2 independent variables giving the value of a dependent variable. And for that, all you do is just separate with a comma. Just you're going to put the 2 independent variables where the independent variable would go, separated by a comma. So define the function, the cost function, in this line with the red box. Define the cost function in the line with the red box. Everyone do that. So it's nice and quiet in here. Does that mean everyone's getting it? You got it? All right, can I have a volunteer to tell me what I should type in to define the cost function? Aiden. How do I do of? Control 9. Capital W. Capital L. So two independent variables now. That shouldn't throw us off. That's no problem. Okay.
And that whole thing's going to be equal
Equals who?
our equation of top.
Okay. I don't know if you can cut and paste. Can you copy and paste from text into a line? I don't know. We'll try. Didn't work? That'd be nice, wouldn't it? No, didn't work. Okay, so I can just do that. So 4 LW plus 288 over L. Is that right? Plus 96 over W. What's that?
Because my graph is like taking up most of my screen, so I have to keep some.
We haven't graphed anything yet, but just grab on the top where there's a little dot and pull it down. Okay, so now you have, now we'll do number 3 together and then the rest will be on your own. I want to use your function to represent and to compute the same quantity as in number 1. So now you're going to use your function to do it. So how can you write an expression now that you have this function that's going to do the exact same thing that number 1 has done? So we want to apply what we've learned. Okay, so this is applying what we've learned. Go compare with the person next to you. Everyone try it by yourself. Try it by yourself. I want to apply what we've learned about functions to recreate question number 1, but now using our definition, or using the function we defined. Wait a sec. Okay, so this is the order here is important. Okay, so make sure you notice that in the table it was L came first and W, and then this is perfectly fine just as long as you know that we put W first in the function comma L. So that's fine. Just be aware of it. That matters. Okay, that matters. So I want to let's walk around and see how you did on this. Did it? Where's TC? Oh. Sure. Just text. So you're going to do Command T. Okay, so I saw some were getting it, some weren't. So we come up here and we say, what does that represent right there, what I highlighted in blue? What does that represent, what I highlighted in blue? How about someone in the back? Yeah. No. That's not my question. The question is, what I've highlighted in blue, what does it represent? What quantity does it represent? Cost of box 1, right? So now we have this function, and we have this very powerful function notation. How can I represent the cost of box 1 with function notation? Yes, sir? What? Careful, though. So, did you all define your function as w comma L? Okay, so just got to be careful. So that's how I ended up doing on the screen. If you did L comma W, that's fine, but it'll be different. That the order matters. So, do you want to try again? What will it be? For G of 4 comma 8. So what is G of 4 comma 8? This is what we've been talking about for the last 2 days. The cost of the box with width of 4 and length of 8. And look what GC did, what graphing calculator did. It gave us a number, right? What is that number? 188. The cost of box number 1. All right? It gives you the value of it. So GC uses and can work with function notation just the way we're learning it. Just the way we're learning it, okay? So now I want to write, so now if you didn't get it before, now I want you to continue on and recreate the value from question number 1 using function notation. Go, finish it, if you haven't already. The point is, you don't have to ever type the rule in ever again. That's the point. You never have to type the rule in ever again once you've defined the function. You can use function notation to represent your dependent variable. You don't ever have to type that rule in again. So somebody new. How do I finish this to get the total cost? Yes? Is that a question? Or go ahead. So from here, what am I going to do? G plus. Yeah, I'm putting my width first, so 5.9 comma 2.6. Then 7.25. And if you defined your function as L comma W, all your ordered pairs will be switched. Okay? But there it is. Look, same cost, 708.44. So the point is, this function notation, it does awesome work for us. Which do you prefer? This version or the first version? Second, it's compact. We can look at that. We know exactly what it means because we know what the function g is. And then that function notation represents the values that we want according to the rule. And then we can make an expression, and it gives us the value of the total of all 3 boxes. Okay, so there's a great advantage to function notation. And so then as things get complicated, we get into the calculus, we'll have multiple functions and expressions with function notation for multiple functions involved. Okay? So you really have to be confident when you look at function notation, you're thinking the right thing. It's the value of the dependent variable when the independent variable is whatever in parentheses. Okay, now you have a series of questions, 4 through 6, and I put the dimensions again at the bottom, so you don't have to keep scrolling up and down. So I want you to now use your function to complete questions 4, 5, and 6. Go. Get help if you need help, okay? Get help if you need help. How many people are done and confident with all 3 answers? Most. Okay, good. Somebody new, number 4. I want to represent, yes sir?
18 times g of 5.9 6.
He said 18 times g of 5.9 comma 2.6 to represent the cost of 18 type 2 boxes. Agree? is it 3,391.21 and 21 cents. Everyone got that? Okay, cool. Okay, number 5, somebody new. Yes, sir.
G of 7.25, 10 minus D of 4.
G of 7.25, comma 10 minus.
D of 4.
Again, I'm putting my width first. If you had length first, you need to reverse those. So a number 3 type box costs $144 more than a type 1 box. Is that what we got? Nice. Okay, last one. Somebody new. Yes, ma'am.
I did G of 7.25, 10 plus 5. I did minus G of 7.25, 5.
Okay, here's what she said. Comma 5? 10. Here's what she said. Agree with this? So we want the final box, the cost of the final version of the box, minus the cost of the initial version of the box. And so if we're increasing it from 10 to up 5 to 15. And notice, so she put in 10 plus 5. That shouldn't be uncomfortable. That's perfectly legitimate. And actually, there's an advantage to that because you're looking at what we intend to do. It was 10 and we want to increase it by 5. So we could put 15 there, or we could put 10 plus 5. Totally legitimate. Questions on this activity? Okay, so the whole point is to see how much work this function notation does for us. If we define a function, we never have to type in that rule again. We can use function notation to create all kinds of expressions that have meaning, and then the function notation tells us exactly what that meaning is. It's very informative and powerful to do things that we want it to do in terms of representing values of the dependent variable. Questions on that? Okay, open up a new screen. New window. So Command N, or maybe Control N on PC. Is that right? So brand new blank window, like that. You want to save your version of the box problem so you can come back to it? So I have a new situation here. The height of a sunflower is modeled by the function h of t equals negative 0.1 t cubed, which is 1.7 t squared minus 0.6 t, where h of t is the height of the sunflower in centimeters, t days after the seed germinates. The function is only valid for the first 10 days after germination, 0 to 10 days. Okay, so I want to skip right to B. Okay, so A, you can work on at home. We should be good at that by now. So we're going to write to B. So in GC, in that new window, I want you to define the function named capital H. But I don't want you to use C. I want you to use little a as the placeholder for the independent time variable. So you're going to use little a to mean, for us, the time in days. Okay? Define that function on the line. Okay? Oops, sorry. Took it down too fast, sorry. There it is. Everyone define that function, capital H. And the reason we're going to use A and not T is, let me show you why here. So in terms of naming functions and defining variables in GC, there are some symbols that are reserved. Okay, they're reserved, so let's talk about those. Everyone got that in? Okay, it's going in 10 seconds. Get it in there. And then you're going to have to look off your neighbor if you're still not done. Okay? So here are, in GC, there are certain symbols that are reserved, and you don't want to use them just as a variable or a function name that you're defining. So x and y. X and y are reserved to represent the values on the x and y axes. So x and y would be like a prompt to GC that you want to display a graph. Okay? Z is similar. It's for a third axis, for if you're graphing in 3D, so lowercase z. Lowercase r is reserved to stand for radius in polar coordinates. Okay? Theta and phi, you have to type out those, so you probably won't come across those. Those are reserved. And look, lowercase c is also reserved as what's called a parametric variable. You don't want to just use t. That's why I had you use a instead, little a, okay, in your function. And parametric functions you'll learn about in Calc 2. U and v are similar to t, so lowercase u, lowercase v, similar for t, for plotting in 3D. And then e, pi, and I have their constant values. Those are parameters, right? Letters that represent non-changing quantities. And so those have their value. You don't want to use those as variables. And then lowercase n, have we seen that before? So n, when you use lowercase n, it opens up an automatic slider. It opens up an automatic slider or a controllable variable that the user can control the value of the variable n. So when we're defining names of functions and parameters and variables, we want to avoid these symbols. We want to avoid these, okay? So you should have defined your function this way, okay? So now, what if I were to come along here and say, so I want to display the graph of this function. Don't do this. Don't type anything, okay? Don't type anything. If I hit graph, will this display the graph of this function? Don't try it. You want to think about it. Will this display the graph?
No.
Okay, why not? Okay, yeah, so we need x and y, right? We want our independent variable we want to put on the x-axis, and that's x in graphing calculator, and then we want to show the dependent variable as y. So to graph it, we need an x there. What will this do instead then? So actually, the way that graphing calculator interprets lowercase a is different in the first line versus the second line. In the first line, we're using it as the placeholder for the independent variable. So it's going to look anywhere in that rule where there's lowercase a. When you do h of something, it's going to take that value and it's going to substitute it wherever there's an a in the rule. Okay? So it's just a placeholder. But now if I use a, now I'm using a as a variable here. It's no longer a placeholder because I'm saying I want y to equal h of a value of the dependent variable. So if you haven't defined what a is, its default value is 1. So in the second line, GC takes little a to be 1. In the first line, it's just saying, oh, I know what you're doing. You're just defining a function, and that's your independent variable. But in the second line, it's going to say, oh, I need to find the value of a. Oh, you haven't defined it, so I'm just going to call it 1. So what is this going to graph if I do y equal h of a? What's the graph going to look like? Okay, straight. All lines are straight. So what kind of line? Horizontal line, right? So it's going to graph a horizontal line at the value of h of 1. See it? And it turns out that the value of h of 1 is coincidentally is 1. It's not graphing 1 because a equals 1. It's graphing 1 because if you plug 1 into that, you also get 1. All right? So if you plug h of 1 equals 1, coincidentally, that's just a coincidence. And so it's graphing that value of the height. But for all x values. So we want the actual graph, so we should do y equals h of x. Okay, but this is supposed to be the height of a sunflower, so this is only valid for x between 0 and 10. So how do we tell graphing calculator just to display it from 0 to 10?
comma 0 less than or equal to x less than or equal to 10.
We've done that before, right? We just want that part of this function where it's valid. Okay, and now we need a better view of this. So we can zoom down here in the lower left corner. So we want to zoom out. So it looks like we've got a good x-axis there. So really we want to zoom out on what? On the y-axis only. So by using the, on Mac, it's the Option and Command keys. On PC, it's, I'm sorry, is that? Yes. On PC, it's the Control and Shift keys that allow you to zoom in on either one particular axis. So I want to zoom out on the y-axis. So for Mac, that's Command. If you hit Command and hold it down, you see that those zoom in and out are now arrows. So I want to zoom out. That's the first box. Zoom out one more time. So that's a decent view of it. But say I also want to zoom in. I want to zoom in or zoom out once on the x-axis as well. So I'm going to go to Option now and hit Zoom out. So whatever. So now we're getting some good views of it. Whatever. Maybe I'll zoom back in once on the vertical axis, and maybe I like this view the best. So I've got my horizontal axis showing 2, 4, 6, 8, a vertical axis showing 10, 20, 30, 40, and maybe this is the view that I like the best. So can you reproduce that view? So everyone try to reproduce that exact view with the scaling on the x-axis and y-axis the way I have it. Can you get your graph to look just like that with the same scales on your axes? Okay, so we still have kind of the most important part of the conversation left here. So I want to move on. So this last part of class, let your attention increase, not decrease, okay? So when you're looking at a graph like this, so it could be this sunflower or it could be a different graph, that red curve, what are you looking at? So this could be any two quantities, right? So it could be cost of the box, it could be distance and time of a runner, it could be the height, anything. But so when you're looking at that red curve, what are you looking at? This is crucial that you have the correct image of what you're looking at when you look at a line or a curve. What are you looking at? Somebody new. Way back in the corner. Oh, is that a question? You just need help? You just need help, okay? Yeah. Okay, she says a series of points. Yes. That's exactly what you're looking at. So when you, let's see if I can get this. When you see that, you want to think this. Everyone look at the screen. You see that, you think this. Okay? It's not a wire that we can change and move around. It's a set of points. Okay? And so when I come here to, back to this. If I come along here and I draw a dot right there, did I just add a point to the graph? Did I just add a new point to the graph? What did I do? So all I'm doing is highlighting a point that was already there. There's a point there, all right? And I tried to draw it at x equals 4. So what does that point represent? So if the whole graph is a series of points, then we need to be really confident we know what every point represents. So what does that point, now we're back to this is the sunflower problem, and I tried to get that point at x equals 4. What does that point represent? Yes, sir?
The height in centimeters at 4 days.
Okay, so the height and center, okay, so can I write the coordinates of that point? What would the coordinates of that point be? 4. I want to write the exact height. I want to write the exact height of the sunflower at 4 days. Somebody knew? Yes, sir? Nope. I want to write the exact height at 4 days. H of 4. Okay, so he answered that this point represents the height at 4 days. That's really, really, really close. But that point does not just represent one value. So he included the other value, but he said it represents the height. In essence, he said it represents the height. That point does not represent the height. What that point represents is the value of time and height taken together. It represents a value of time and height taken together. So by saying it represents the height at time equals 4, it's like so close, but it's not just the height. It represents the simultaneous values of these two quantities. Okay, so it represents that when time is 4, the height is h of 4. When time is 4 days, the height is h of 4 centimeters, or whatever we said. Where on this graph is the representation of actually the height at 4 days? Where do I look for the actual representation of, yeah? Right, okay. So h of 4 is actually represented, just by itself, is actually represented, right there. So that's where we could get an estimate for it. So, I'm guessing, let's see, it's about, 17.5, or no way, I was way too low there, sorry. Let's look up here, right? One more try. So I'm going to guess it's about 18. So we can get an estimate, but if we want the exact height, what do? We want to get the exact height. Yeah? Well, yeah, so we want to get the value of h of 4 using the rule, right? The rule will give us that value, okay? So, now there's one more aspect of this. Not just that you see this and you think this, but there's another aspect of this. What did we say about variables? What are variables? Letters that represent changing quantities. Variables vary. So an even better way to think about this, okay, the very best image you can have to think of this is this. This is the very best image you could have when you see a graph. It's how points emerge as the independent variable varies. Okay, so we think about time increasing, and as time increases, every moment in time is generating a coordinated point of time and height. So when you see a graph of a curve, this is the strongest image you could have to think when you see a graph is the revealing of all the coordinated points as the independent variable increases. Okay, check Blackboard for all the details on homework.
Yeah, that's the rest of the things. Graduated
That's right. Okay. So you just need to sign up, do whatever you need to do, and then I should get the email. For the contract.
For that, should I just write down?
Yeah, just write like a